spokesman for the meeting said that the price pause would give the Western world a chance to show their good intentions. What he meant was whether they could stop inflation of the prices they charge OPEC countries for their industrial exports. Unless something's done on these lines, the message from Geneva today is that there will be another steep rise in oil prices after next April the 1st.
The turmoil and uncertainty caused by the 1972 oil crisis placed new emphasis on the need to search for alternative fuels and to exploit renewable energy resources. Silicon solar cells developed for the space program provide an attractive possibility: the conversion of sunlight directly into electricity. These semiconductor devices are now being used to provide electricity in remote locations where more conventional forms of generation are not viable. But the more efficient single crystal cells are still too expensive. And cheaper variants, amorphous silicon cells, familiar in solar-powered calculators, and polycrystalline silicon cells are too inefficient to compete in situations where other forms of generation are viable. But silicon solar cells and alternative photovoltaic devices using different semiconductors are not the only way to generate electricity directly from sunlight. An entirely different approach has been developed by the Swiss chemist Professor Michael Grätzel. The research that led to photoelectrochemical cells like these, which have been driving themselves round for the last 2 years, embraces a wide range of different aspects of chemistry and stemmed from an attempt to mimic plant photosynthesis with the aim of synthesizing alternatives to fossil fuels. Plants use sunlight to synthesize the chemicals they require for growth. The leaf's green color is a clue to its light harvesting mechanism. It's the outward sign of special cells that are packed with green chlorophyll molecules. These capture photons of light, channeling their energy to reaction centers on the inside of the cell membrane, where it excites electrons. Each excited electron is transferred from the reaction center through a chain of proteins to the outside in less than 1,000th of a second. But because the electron transfer reactions become progressively slower along the chain, it's an effectively one-way process. The reaction center regenerates by picking up electrons from the solution contained by the membrane, and in so doing, liberates oxygen. In effect, this light-induced process of charge separation cleaves water across the membrane. There are 3 distinct processes at the heart of photosynthesis. Light harvesting, the capture of photons to produce excited electrons. Charge separation, the transfer of these electrons across the membrane. And regeneration, the reduction of the positively charged photocenter so that it is able to produce a further excited electron.
We have to mimic the chlorophyll molecules that absorb sunlight. So we use a photosensitive compound. There are plenty of those around, but unfortunately, when you put those in solution, nothing will happen. Light will come in, the light will be absorbed, but the electron that is photo-ejected from the molecule will return immediately back, and so there's no overall effect of light. And so what you really need to do is to mimic the membrane, photosynthetic membrane, which is the molecular organization provided by the plant to achieve charge separation. And that part we mimicked by using surfactant micelles. Micelles are formed by detergent molecules.
Detergents dissolve oily materials through the action of surfactant molecules. These attach their hydrophobic tails to the oil surface, forming micelles, tiny oil droplets encased in surfactant molecules whose hydrophilic heads form an external water-seeking surface.
Our idea was to use the micelles to solubilize the photoactive compound in an aqueous environment, providing a molecular organization that would sustain charge separation. And when we illuminated those samples, they turned green, while without the micelles, nothing would happen. And the green color indicated that charge separation had taken place and that hydrogen was evolved from the electrons ejected from the micellar into the aqueous phase.
So the sensitizer-filled micelles mimicked photosynthesis in harvesting light to give an excited state, and in preventing the released electron from recombining with S+ by passing it through the surfactant shell and into the aqueous phase where these electrons reduce water to hydrogen.
Of course, immediately thought that that might take us a long way towards the goal of achieving water cleavage, that is, the dissociation of water into hydrogen and oxygen by visible light. But of course, quickly we realized that there's no recycling, the oxygen part is missing, and that at some point this reaction will stop.
In this light harvesting reaction, a photosensitive compound within a micelle is excited by a photon, and then forms S+ and an electron which takes an effectively one-way path to the outside of the micelle. Here, electrons react with water to give hydrogen gas. Eventually, the reaction stops as S is used up. To achieve continuous water cleavage, Grätzel had to find a way of making the reaction cyclic, reducing S+ to S, and in so doing, oxidizing water to oxygen. At the time, their best photosensitive compound was tetramethylbenzidine, TMB. So they turned the focus of their research to finding ways to reduce TMB+ with water to TMB. The oxidized sensitizer TMB+ didn't react spontaneously with water, so they set about looking for substances which might catalyze the reaction. This search led them into a new field, colloid chemistry. Colloids are such finely divided solids that they stay suspended in a liquid rather than settling out. Their significance lies in the huge surface area they present on which reaction can take place. When the equation for the oxidation of water to oxygen is balanced, it's apparent that 4 TMB+ have to react with 2 molecules of water. Such reactions usually proceed by a series of intermediate steps, and the success of the overall reaction is greatly enhanced if the reactants can be held in close proximity. A colloid provides such an environment. TMB+ ions are absorbed on the colloid surface where they can react with water in a stepwise fashion. In practice, the search wasn't so simple, for not all colloids facilitate the reaction. It took Grätzel's group 3 years before they found a colloid which efficiently promoted the reaction, oxidizing water to oxygen.
To our great relief and joy, the reaction was working. There was a problem in as much as the TMB wasn't absorbing in the visible. It just harvested the ultraviolet portion of sunlight, and that's not enough. To get a reasonable yield, you have to harvest visible light.
So now Grätzel's research focused on replacing TMB with a dye that could be absorbed onto a colloid, where it would harness the energy of visible light to cleave water into hydrogen and oxygen.
Light level here.
They were at last making good progress in the search for suitable dyes when news was received of Japanese work that would change the direction of Grätzel's research. The Japanese had succeeded in making an electrochemical cell in which water was cleaved by ultraviolet light. In such a cell, hydrogen is produced by the reaction with water of electrons flowing into a platinum electrode. The unique feature of the cell lay in the illuminated electrode which produced oxygen. This was formed from a single crystal of the semiconductor titanium dioxide. Electrons within the semiconductor are usually fixed in bonds, but they can be excited to a higher energy state, the conduction band, where they are free to move. The energy required for the transition is supplied by ultraviolet light. Once in the conduction band, the excited electrons flow freely into the external circuit. This leaves the titanium dioxide electrode short of electrons, which it replenishes by extracting them from water, oxidizing it to oxygen. While a substantial achievement, this experiment had a problem.
We realized that the problem with that experiment was the same we had with TMB. In other words, this system was not sensitive to visible light. Hence the idea of using a dye stuff, such as chlorophyll, to harvest the visible light in conjunction with the colloidal titanium dioxide particles.
Two important parameters were measured to gauge the efficiency of charge separation for many different combinations of dye and colloidal titanium dioxide. The yield, which relates the numbers of electrons promoted into the semiconductor's conduction band to the photons absorbed by the dye, and the relative forward and backward reaction rates for electron transfer, a measure of how well the combination prevents the promoted electrons from recombining with the oxidized dye.
We realized quickly that the yield for charge separation was greater than 50%. And moreover, the relative rate for forward and backward reactions were very different. The forward reaction was 1,000 times faster than the backward reaction. But there was still this problem of recycling the dye. In other words, the oxidized state of the dye had to be brought back to the original state. And in doing so, one would have to oxidize water to oxygen. And it was while I was listening to lecture in Belgium about thermodynamics of water cleavage that I realized how powerful an oxidant one really required to achieve this reaction. And so in screening different possibilities, we selected a ruthenium compound that had groups, chemical groups attached that would make it a very powerful oxidant. Now, when we tried that, we found the most brilliant result. Not only was the yield of charge separation very high, greater than 50% this time, we had a 1,000,000-fold difference in the forward to backward reaction rate. And so we came very close to what the natural photosystem of the plants achieved. In other words, very favorable situation kinetically as far as light-induced charge separation is concerned. We realized that although this system was active in producing electrons and oxygen from water, there was a problem with competing reactions. In other words, the injected electron preferred to react with the oxygen that was produced from water instead of reducing water to hydrogen. And so the yields that could be achieved in the overall water cleavage reaction were very small.
The use of electrodes to collect the charge and a more conventional cell setup in which the hydrogen and oxygen could be kept separate provided the solution to this problem.
The experiment I suggested to my student was to use a titanium sheet, oxidize it, and try whether the dye stuff that was so successful on the colloid would also work on this titanium dioxide electrode. Well, when a student came and reported to me that he had observed a few microamps of current, he wasn't very impressed, but I thought about these data, and it appeared to me that we had something interesting there, because colleagues that had done experiments of the same type had seen only nanoamperes in current. And so there was something interesting that was worthwhile pursuing. And that's what we did. We tried to then capitalize on this finding and develop electrodes that would have a more active surface area than the ones we had produced from the mere oxidation of a titanium sheet. And by coincidence, I met with a colleague who suggested a method to get high surface area titanium dioxide films. And so we went ahead and tried these new type of electrodes. The surface area increase was about a factor of 100, and these electrodes would yield in sunlight about a milliamp or two photocurrent. This was so much better than what people had observed earlier that we decided to publish these results. And the work was accepted and published in the Journal of the American Chemical Society in '85. We realized, of course, that we were making electricity from light at this stage, so we had gone away from our first goal, that was the split water by sunlight. But of course we hadn't abandoned it, we were just concentrating on this particular part. And so the next question was, could we bring this cell into a configuration where it was to be used practically? And now you might envisage easily that if you have a titanium sheet covered with an oxide film and a counter electrode, and you bring that in a sandwich type configuration, that no light will come in. Hence the need to make at least one of those electrodes transparent. And this was the point where we started to put down the rough titanium dioxide film on conducting glass. So the light could go through the glass and be absorbed by the dye stuff that was adsorbed on the film of titanium dioxide. The overall efficiency was around 4% at this time and comparable to amorphous silicon. We have tried to improve on that, and this was done in two ways. On the one hand, we improved on the thin film technology. We used the colloidal particles, the ones we had been studying solution. We used those now to make films, and that technology allowed to further enhance the surface area by another factor of 10. So instead of having 100-fold increase in surface area, we now have 1,000-fold. And that helped, of course, with the light harvesting. In parallel, we developed better sensitizers that would cover a broad range of the visible. And at the present stage, we are at the point where the sensitizers start to absorb all photons below 750 nanometers. And that's fairly close to the optimum of 880. So the improvements have been on two lines, one being the thin film technology, the other being the dye stuff technology. In order to understand the operation of this cell, we have to consider the electronic energy levels. An easy way into that is by an analogy. The farmer here on the mountain with the sun, the rocks he's throwing are the photons that come down to the earth. We have the sensitizer presented here as the electron lake. So the rock that comes in excites electrons. These are presented as water droplets. So the water droplets will be splashed up onto the roof and run down to the gutter, which is the conduction band of the semiconductor. And from there on, it will run down, perform work by turning the wheel and return to the electron lake. Now, of course, the low energy photons will produce droplets that won't go up to the roof at all, so they're not contributing to the photoelectric effect, while high energy photons will produce droplets that go up very high. Now, if you want to collect all the droplets that splash up, you would place your gutter at a very low level, but then you realize that the work you can do will be very small. And although you will draw an extremely high electric current, the voltage will be low, and hence the output of the cell will be small. Conversely, if you place your gutter too high, then very few of these droplets will be caught, and hence your current flow will be low. So there will be a positioning of the gutter where the output of the cell will be the best combination of current and voltage.
Here, the functioning of the cell is shown in terms of an energy level diagram. Starting with the sensitizer dye S in its electronic ground state, a photon of visible light excites it to an energy that is high enough for the electron that is released when it forms S+, to fall into the titanium dioxide semiconductor's conduction band. The electron moves through the semiconductor in the conduction band to be collected by the conducting glass backing and fed into the external circuit. Here it drives an electrical load, and thence is fed to the conducting glass counter-electrode. An electrolyte is needed to shuttle electrons from the counter-electrode back to the photosensitive electrode, where they reduce S+ back to S. The electronic energy level of the electrolyte is critical to the efficient functioning of a practical photoelectrochemical cell. If it was high, close to that of the conduction band, no power could be drawn from the cell, as the open circuit voltage depends on the difference in the two levels. The voltage would be increased if the level were lower than the sensitizer's ground state, but then no current could be drawn from the cell. For energy would be needed to raise the electrons from the electrolyte to the sensitizer energy level. The optimum in cell design is to have the energy level of the electrolyte just above that of the sensitizer dye's ground state. But there's another factor that's vital in the choice of an electrolyte for a durable, practical cell. Its long-term chemical stability.
In the earlier days we used the bromine-bromine redox system. This turned out to be not satisfactory because bromine is volatile, very reactive. So we changed, and we are using iodine iodide now, which is very good and very stable. Same considerations apply for the sensitizer, the dye stuff. Many hundreds of dye stuffs have been tested, but only a few turned out to have the tremendous stability required for this application.
The success of the various changes over the years can be seen in the steadily increasing solar conversion efficiencies of the cells. At present, the cells are more efficient than amorphous silicon solar cells and approaching the efficiency of the better single crystal cells, but at 1/5 of their cost. So where does Grätzel expect his cells to be used?
Anywhere where you need a translucent see-through glass that would produce electricity, this technology has no competition. The other more demanding line of development will be the high energy market, where you want to go to the kilowatt, 10 kilowatt range, and there we still need to do development. Some of the technical steps have to be implemented. But I think once we have a kilowatt up there, we will be convincing for the engineers.
Only time will show whether or not these cells have a long-term future. But whatever else, their development is an example of the tortuous path research often takes, and of the persistence, knowledge and vision needed to follow it through.